So in this problem, we're given a situation that looks like this. We have a large disk of mass big M, radius big R, and a small child of mass big M is thrown onto the disk with velocity v. The child lands and sticks to the disk at a distance little r from the center of the disk. And in part A, we're asked which of the three of linear momentum, angular momentum, and energy are conserved in this situation. So first, looking at linear momentum, we can see that there are no net external forces on the system of the child plus disk, and so linear momentum has to be conserved. Looking at angular momentum, there are similarly no net torques on the system of disk plus child, and so angular momentum has to be conserved. However, energy is not conserved. And the reason for that is that when the child lands to the disk and sticks to the disk, there's going to be some internal energy that's lost to heat or deformation of the disk, and so that energy is just going to be lost, and so kinetic energy cannot be constant throughout the collision. Now in part B, we're asked what the final velocity of the center of mass of the child disk system is going to be. And we can solve for this using the fact that momentum is conserved. So we know that P initial equals P final. We know that P initial is m times v, the velocity of the child, and that is equal to the final mass of the system, which is just big M plus big M equals 2m times v cm. So then VCM is equal to 1 over 2 times the initial velocity of the child. Now for part C, we're asked to find what the angular velocity omega of the system is going to be after the child sticks to the disk. And we're going to solve for this essentially the same way we solve for angular momentum, or the same way we solve for velocity here, is we're going to use the fact that angular momentum is conserved. So angular momentum initial equals angular momentum final. However, you might initially sort of intuitively want to set angular momentum initial to be calculated about the center of mass of the disk, because that's where it seems like things are going to kind of rotate around. It gives you a convenient radius to use when you're calculating the angular momentum of the child. However, that's going to be not the way you want to do that. And the reason for that is that there are, remember, two different kinds of angular momentum. We have orbital angular momentum and spin angular momentum. And if we calculate about the center of mass of the disk, then both of those are going to be more complicated than they have to be. However, if we calculate this about the reference point right here, the point where the child lands on the disk, then we have that the initial angular momentum, L sub I, is 0, because the velocity vector of the child is pointing radially inward towards the reference point. And what that means is that the orbital angular momentum and the spin angular momentum have to be equal and opposite. They have to cancel each other out. And so that's how we're going to solve for the angular velocity omega of this system. So L final is going to be the orbital angular momentum plus the spin angular momentum. So that's r cross p plus I prime omega. Remember, all of these are vectors. So r cross p is going to be using the distance to the center of mass. So the center of mass of the system is going to act as if we have a point mass at this point right here, which we do. It's the child with mass big M. And then the center of mass of the disk is at this point right here. And so that also has mass M. So what that means is that the center of mass is exactly halfway between them at a distance little r over 2. So RCM here is little r over 2, and then crossed with the momentum. The momentum is, remember, we have now the full mass of the system, so that's 2m, times the velocity of the center of mass is v over 2, so that's v over 2. And then the angle between r and p is 90 degrees, so we don't have to worry about sine of theta. Now for I prime, we're going to have to calculate the moment of inertia about the center of mass. And so that's going to be, first of all, we have m times r over 2 squared. That's the moment of inertia of this point mass, the child sitting at that point. And then the moment of inertia of the disk is we're going to have to use the parallel axis theorem. So that's going to be 1 over 2 mr squared for the moment of inertia of the disk rotating about its center of mass. And then we're going to have to shift that by a distance little r over 2. And so that shift is going to give us another term of m little r over 2 squared for the moment of inertia, and then this is going to be multiplied by omega. So what this tells us is that, and remember that the orbital angular velocity, r cross p, we're going to have to give it a direction, because remember all of these are vectors. So r points upwards, because from this point right here to the center of mass points upwards, and then p points to the right. So if we use the right-hand rule, that tells us that the orbital angular velocity points into the page. So then we can solve for these because these two have to be equal and opposite. This tells us that m r squared over 4 plus mr squared over 4 plus 1 over 2 m big R squared times omega is equal to, multiplying this out, we get mrv over 2. And then it has to be in the opposite direction, so this is going to be pointing into the page instead of, I'm sorry, this one is pointing into the page. Because remember, right-hand rule, that was into the page, so this one's got to be pointing out of the page. So that tells us that then we can solve for this and pull this over, and we get omega. This term is going to be 1/2 m times big R squared plus little r squared. So this is going to give us mrv over 2 times 1/2 m big R squared plus little r squared. Close both sets of parentheses. These 2's are going to cancel out, and the m's are also going to cancel out, and this is going to give us omega final is equal to rv, and I just added this vector there, rv over big R squared plus little r squared pointing out of the page. And so as our final answers, we get that linear momentum is conserved, angular momentum is conserved, energy is not conserved, the final velocity of the center of mass is 1 over 2 times v initial, and the final angular velocity is rv over big R squared plus little r squared pointing out of the